The HVAC industry sells you a $15,000 system that costs thousands every year to run. But over 1,000 years ago, engineers in Persia built towers that cool interiors by 15 degrees using nothing but water, air, and gravity. No compressor, no electricity bill. That technology was never disproven. It was buried. And the story of who buried it and why starts in the desert city of Yazd. In Yazd, Iran, the skyline bristles with over 700 wind towers, badgirs, each a testament to centuries of climate-responsive engineering. These towers are not relics or myths. They are measured, mapped, and monitored. Municipal surveys and university researchers have documented their performance for decades. The most dramatic example, the Ahmedabad Garden Tower, stands at 33.8 meters. On summer days when the desert air outside hits 40 degrees Celsius, the rooms beneath a functioning Badgir remain at 25 degrees Celsius. That is a drop of 12 to 15 degrees, confirmed by Internet of Things sensors and field studies as recently as 2019. The effect is not a one-off or a legend. It is a repeatable, quantifiable result, a temperature differential that mechanical systems would struggle to match without burning through kilowatt hours. Professor Hamid Rakhshande of Yazd University puts it plainly: the Badgir is not merely a ventilation device, it is a cultural artifact that embodies centuries of climate-responsive ingenuity. In Yazd, the evidence is not buried in ruins. It is alive in the city's daily life, and the numbers leave no doubt. The results are real, the science is solid, and the system works exactly as designed. Hot, dry air carries a hidden opportunity. When it passes over water, something remarkable happens. Evaporation pulls heat from the air, dropping its temperature toward what scientists call the wet bulb limit. This is not a minor effect. Evaporating just 1 kilogram of water absorbs about 2,500 kilojoules of heat, enough to chill a room without a single watt of compressor power. In a downdraft cooling tower, gravity does the rest. As the air cools, it grows denser and heavier, falling naturally down the shaft, sweeping fresh comfort into living spaces below. No motors, no fans, just physics and a bit of water. The process is governed by universal laws, not local legend. The temperature drop is set by the difference between the dry bulb and wet bulb readings, a gap that can reach 15 degrees Celsius in desert climates. This is the same principle that drives historic badgers in Iran, malqafs in Egypt, and even modern research towers in India. The underlying science holds true from ancient courtyards to contemporary labs, wherever air and water meet under the sun. From the Nile Delta to the Deccan Plateau, passive downdraft cooling emerged independently in some of the world's hottest, driest climates. In medieval Egypt, the malqaf became a staple of palace courtyards and city homes. Archaeological surveys date these wind-driven shafts to at least the 12th century, with surviving stonework and carved reliefs showing their role in channeling air over water pools to cool interior spaces. The same principle appears under different names: Shaduf-linked coolers in the Levant, Tara towers in North Africa, Mongol roofs in Rajasthan, and water mist roofs in Bangladesh. These are not local oddities or unproven myths. They are evidence of convergent engineering. Across regions and centuries, builders arrived at the same solution: harness water, wind, and gravity to beat the heat with no moving parts and no electricity. Before the age of compressors and refrigerants, these passive systems were the dominant answer to extreme summer temperatures. The universality of the design, confirmed by archaeological fieldwork and medieval records, leaves no doubt. Passive downdraft cooling was the default for comfort in arid zones, not a regional experiment or a forgotten footnote. In 1902, Willis Carrier filed a patent that would quietly upend the logic of building comfort. His invention, the first modern air conditioning system, was designed not for homes or theaters, but for a Brooklyn printing plant that needed to control humidity for ink and paper. Yet by the 1920s, Carrier's technology had found a new market: human comfort. Manufacturers launched a wave of advertising campaigns, selling the idea of electric cool to department stores, movie palaces, and middle-class homeowners. Early product brochures promised a future where summer heat was tamed by the flip of a switch. The mechanical system's appeal was not just in its performance, but in its business model. Unlike the passive towers of Yazd or Cairo, which required a one-time investment and minimal upkeep, Mechanical air conditioning demanded a steady stream of electricity, regular maintenance, and eventual replacement. Each unit installed meant a new customer for utilities and a new service contract for HVAC firms. Carrier's 1902 patent and the consumer push of the 1920s laid the groundwork for a profit-driven shift in building science. The industry's embrace of compressors and refrigerants was not a neutral evolution. It was a pivot towards systems that generate ongoing revenue, locking out solutions that worked too well to meter. After World War II, a coalition of HVAC manufacturers and electric utilities set out to make mechanical cooling the default in American buildings. Their influence reached deep into building codes and professional standards. By 1962, the International Residential Code included language that required forced air mechanical cooling in so-called cooling-dominant regions. The wording was not accidental. Model code committees, often staffed by industry representatives, inserted clauses that made it nearly impossible to get a permit for anything but a compressor-driven system. The National Air Conditioning Manufacturers Association and the Edison Electric Institute funded advocacy campaigns, producing studies that claimed passive designs would threaten utility revenues by cutting peak summer demand. These reports became the backbone of code revisions throughout the 1970s and the 1980s, locking in mandatory AC for millions of homes. The educational pipeline was quietly redirected. Between 1965 and 1975, surveys show that over 80% of accredited architecture programs dropped their courses on passive climate design. In their place, new electives on HVAC systems design became the norm. Textbook publishers, under pressure from industry sponsors, removed chapters on wind catchers, earth tube ventilation, and evaporative cooling. By the late 1970s, most new architects and engineers graduated without ever learning the principles behind these systems. The alliance between manufacturers, utilities, and code bodies didn't just tilt the playing field, it paved over the competition, ensuring that passive downdraft cooling would be sidelined, not because it failed, but because it worked too well for anyone's bottom line. At the Torrent Research Center in Ahmedabad, passive downdraft evaporative cooling is not just theory, it is measured, metered, and proven on a scale that mechanical systems struggle to match. Over a 15-year monitoring program, the TRC tower, 20 meters tall, cut electricity use for cooling by 68% compared to a conventional HVAC baseline. The system, which cools a 10,000 square meter facility, relies on nothing more than water, gravity, and solar-powered pumps. The payback period for the extra construction cost, about 7% above a standard roof, was between 5 and 7 years. Dr. Anil Patel, the lead engineer on the project, said it plainly. Our data proved that a 20-meter tower can replace a 5-ton split-system air conditioner, cutting electricity use by 2/3 while delivering comparable comfort. These numbers are not outliers. They are the result of continuous submetering and third-party audits. The TRC case stands as a direct contradiction to the claim that passive cooling is obsolete or unproven. The evidence is modern, robust, and impossible to ignore. Regulatory language does more than shape blueprints. It decides what is allowed to exist. California's Title 24, for example, requires that new homes in key climate zones install a central air conditioning system approved by the state's equipment tables. The code does not offer a true performance-based alternative for evaporative towers. Even the passive cooling credit excludes most water-based downdraft designs by demanding humidity controls and verified airflow rates that only mechanical systems can easily provide. For homeowners, the math is stark. A standard central air conditioning system now costs between $15,000 and $20,000 installed, with ongoing electricity bills and future compressor replacements. A whole house evaporative cooler, by contrast, ranges from $3,000 to $7,000, and its annual operating cost can be as low as $50. The payback period for passive systems lands at 5 to 7 years, sometimes less with utility incentives, while central air conditioning can take more than a decade to break even. Yet because prescriptive codes block passive towers from permits, and lenders will not finance what is not code compliant, the cheaper, low-energy solution is sidelined before it starts. A rooftop downdraft tower is not just for ancient cities or high-tech labs. Homeowners like James Martinez in Phoenix have built their own for less than $400 in materials. His kit started with galvanized steel pipe, PVC misting nozzles, an insulated 200-liter water tank, and a small pump, each item off the shelf at a hardware store. The assembly is straightforward: cut the shaft, attach the pads, fit the misting heads, and connect the pump to a basic water reservoir. For those looking to push performance further, a buried ground-coupled intake pipe, about 30 meters long, can be added for an extra $100 to $200. This upgrade taps the cooler subsoil, boosting airflow and dropping intake temperatures even more. Martinez reports that after a weekend's work, his first summer saw a $380 cut from his cooling bill and a home that stayed silent and comfortable, no compressor required. The path is clear. With $200 to $400 and a few hours of labor, anyone can reclaim a system that delivers comfort without the meter running. A system proven to cut cooling costs by 68% with a 5-year payback and near zero lifetime bills was sidelined, not for failing, but for threatening the profit model of $15,000, HVAC units, and endless utility fees. Some knowledge isn't lost, it's buried. Subscribe for more truths they never taught in school.